Welcome back. In this lecture, we will cover the development of potential flow by superposition of elementary flows. We had in the last lecture done the basic potential flow solutions for a uniform flow, a source, and a free vortex. Since the Laplace equation and the applicable boundary conditions are all linear in the dependent variable phi, the potential flows in complex geometries can be obtained by superposing the potentials for the simpler flows. One of the more important principles used in this process is the fact that flow is always along a streamline with no component across it. This permits us to replace any streamline with a solid wall without affecting the flow in the rest of the region. Thus, if we plot the stream functions psi is equal to xy, we get rectangular hyperbola in all the four quadrants. Now, in this first picture, we have replaced the x-axis with a wall so that psi is equal to xy represents the flow in the upper half plane, the flow directed towards the wall perpendicularly. In the second picture, we have replaced these parts of the axis with walls so that the same stream function represents the corner flow into one corner. In the third picture, we have replaced this streamline with a wall. And if we do this, the same stream function represents the flow over a body of this shape. In the last picture, we have replaced two streamlines with walls so that now psi is equal to xy represents the potential flow through this channel formed by these two walls. If a streamline forms a closed contour dividing a 2D flow region into two parts, one inside the contour and one outside, we could imagine a 2D body occupying the inner region. The streamlines in the outer region then represent the flow about that two-dimensional body. Thus, the internal portion of this could be replaced by a body, and then the same stream functions and potential function represents the flow about this body. These are the principles that we use in generating flows through superposition. If we have flow adjacent to plane walls, then these can be constructed by considering appropriate image system. Thus, if we have a source close to a wall, then we can consider an image source as prime. The original source would induce a velocity like this at this point, while the image source would induce a velocity like this. The horizontal components of these two velocities cancel, resulting in the straight line of this wall, the vertical line, being a streamline. And this streamline could be taken as a wall. So then the resulting potential function or the stream function would represent the flow due to a source situated very close to a wall. This would be the pattern of streamlines for a source and its image, and we could cover the left portion to result in a flow due to a source near a wall. The potential at point P can be written as the potential due to source at x is equal to a and y is equal to 0, and at x is equal to minus a and y is equal to 0. Combination of the two potentials. This is the resulting flow due to a source situated very close to a wall. Similarly, we might have a vortex sitting close to a wall. To construct the potential for this, we imagine an image vortex situated on the other side of the wall at equal distance. The induced velocity because of this vortex is this, while the induced velocity because of this vortex is this. No normal component of velocity, so the wall is a streamline. And we could suppress one portion to obtain a flow like this. This is the potential because of a clockwise vortex at x is equal to a, and this is the potential due to a counterclockwise vortex at x is equal to minus a. Now we combine a uniform stream V naught is equal to V naught I. This is a uniform stream in I direction and a source of strength Q. We take the potential of the uniform stream and the potential of a source and add them two together. Thus, V is equal to V naught X because of the uniform stream plus Q divided by twice pi ln R because of the source, resulting in phi is equal to V naught X plus Q divided by twice pi ln under the root x square plus y square as the potential of a flow which is a combination of a streamline and a source. The stream function similarly could be written in the same fashion. The velocity component associated with these functions are u is equal to del phi by del x or del psi by del y, and they are obtained at v naught plus q divided by twice pi into x divided by x square plus y square. Similarly, the v component. If we take this stream function and plot, we get this shape. For V naught is equal to 1 and Q is equal to 1. Now, this streamline can be taken as the wall of this half body since it extends to infinity on the right. And so then the potential function and the stream function that we obtained in the last slide can be used to represent the potential flow about this Rankine half body. These are the velocity components u and v that we obtained earlier. The point A where the streamline bifurcates must necessarily be a stagnation point. And to locate the point A, we put in the value of u and v both equal to 0 to obtain the value of x and y at which this point occurs. The y coordinate of this point is clearly 0 from this equation, and from this equation for u The x coordinate is obtained as minus q divided by twice pi v naught. Thus, the point A has the coordinate minus q divided by twice pi v naught and 0. For the value of q and v both is equal to 1 for this picture, this point is located minus 1 divided by twice pi and 0 in this picture. Now, the streamline passing through this point is then given by v naught r sine theta plus q theta divided by twice pi is equal to q by 2. From this expression of psi, we put in the value of x and y that we obtain, and when we do this, we get v naught r sine theta plus q theta by twice pi is equal to q by 2. That is, in the xy coordinates, v naught y plus q divided by twice pi, tangent inverse y by x is equal to q by 2. This is the equation of the body contour in x and y coordinates. The maximum half thickness of the body is obtained by obtaining the value of y on this contour when theta tends to 0. Theta angle is measured from the origin. Theta angle is measured from the origin. As theta tends to 0, the point on the body moves to infinity. So, the y coordinate as theta tends to 0 represents half thickness of this Rankine half body at infinity. And this is easily obtained from this equation as y is equal to q divided by twice v naught. So that the total maximum thickness of this half body is q by v naught. We can do all kinds of manipulation once we know the stream function psi and the potential function phi. We can easily obtain the pressure distribution about this body by applying the Bernoulli equation between a point far upstream where the velocity is v naught and the pressure p naught, and a point on the surface of the body at a given x location. Thus, we take a point 1 far upstream where the velocity is undisturbed v naught and the pressure is taken as p naught, and the second point we take is a point on the body surface at a coordinate x. And when we do this, we obtain this as the curve for pressure variation along the x-axis. The minimum coefficient pressure Cp is minus 0.587 and occurs at theta is equal to 64.96 degrees or 0.36 pi radians, that is at x is equal to 0.14 in this picture. The maximum pressure coefficient, of course, 1, and which occurs at the stagnation point A. Let us next consider the flow due to a source and a sink pair. Imagine a source situated on the x-axis at minus a and a sink at x is equal to plus a, both of the same strength q. Positive q for the source and minus q for the sink. Then let's write the potential of this combined flow at a point P at location r theta. This is obtained simply as q divided by twice by ln r1 minus q divided by twice by ln r2. R1 is the distance of the source point from point P, and we use plus Q because it's the source, and R2 is the distance of the sink from point P, and we use minus Q because it's a sink. This is the expression in the xy coordinates. Similarly, we write the stream function. If you plot the streamlines, this is what we get. In this, the flow velocity would be directed like this. Let us superpose on this source and sink pair a free stream velocity V0, a uniform flow V0 in the x direction. Then the potential function and the stream functions are like this. We have added the potential due to the free stream and the stream function due to free stream in the expressions that we had in the last slide. If we plot the streamlines are seen like this. This streamline, which is bifurcating at 2 points, must have stagnation points there, and so we can replace the inside of this streamline with a solid body. This shape is known as a Rankine oval, and so this potential function and this stream function represents the flow past this Rankine oval. We can do all the algebra, we can find the location of the streamlines, we can find out the pressure coefficient about this body. The stagnation points are at minus plus under the root qa by pi v0 plus a square. This is obtained by differentiating phi with respect to x and with respect to y to obtain the expressions for the velocities u and v and equating those two velocities as 0. We will obtain y is equal to 0 for both the stagnation points and x given by this expression. An interesting case occurs when the source and sink pair approach each other. In the same picture as before, the velocity potential phi is given by this expression, where R1 is under root y square plus x plus a whole square, because now the distance is measured from this point, and R2 would similarly be under root y square plus x minus a whole square. And in r and theta coordinates, the expressions are obtained like these. So the contribution of the source, which is q by twice by ln r1, becomes this, and from the radical sign we take r square out, which becomes r, and then inside it is sine square theta plus cosine square theta plus a square plus twice ar cosine theta. And this can be simplified as this. And similarly, the contribution of the sink to the potential function can be written down, and it is similar to that of the source except for this sign change. The two together give this, and if we look carefully, this LNR cancels with this LNR, and we have this is the result, which is approximately QA divided by pi r cosine theta plus terms of order a by r whole square. So if a is small compared to r, this approaches QA divided by pi r cosine theta. In the limit, as a tends to 0, with QA held constant at a value k, the potential function phi at r and theta becomes k divided by pi r cosine theta. In the slide, I have shown 6 different configurations in which the value of k, that is q times a, is held constant, but the value of q is increasing and the value of a is decreasing. And this is the final shape when a has become is equal to 0 with QA held constant at k. This flow is known as the doublet flow, and the potential for this is simply mu divided by r cosine theta. It may be noted that this pattern of streamlines is the same as the pattern of electrical or a magnetic dipole lying on the x-axis and pointing towards the left. So doublet is like a dipole, a positive pole, source, and a negative pole, the sink. The r component of velocity is obtained as minus mu divided by r square cosine theta, and the theta component of velocity is obtained as minus mu divided by r square sine theta. The stream function obtained from these velocity components by integration is minus mu divided by r sine theta. Now, we are interested in doublet because if we superimpose on this a uniform flow, we get the flow past a circular cylinder.